we're asked to use the method of Lagrange multipliers to find the point where the maximum value occurs for f of x comma y equals xy, subject to the constraint x plus 5y equals 64. We will assume the conditions of Lagrange's theorem are met, and therefore if f of x comma y has a max or a min, subject to the constraint g of x comma y equals 0, then the gradient of f is equal to lambda times the gradient of g, where lambda is some constant, and g of x comma y equals 0. The gradient of f is equal to lambda times the gradient of g indicates the max or min occurs where the two gradients are parallel or multiples of one another, and also normal to the level curves of both f and g. The result is, if we solve the system of equations below, we can determine the maximum value of the given function f under the given constraint. So we know f of x comma y is equal to xy. To write the constraint in the form of g of x comma y equals 0, we need to set one side of the equation of x plus 5y equals 64 to 0. Let's subtract 64 on both sides, and therefore g of x comma y is equal to x plus 5y minus 64. And let's work on setting up our system of equations. Let's first find the equation given by the partial of f with respect to x equals lambda times the partial of g with respect to x. To find the partial of f with respect to x, we differentiate xy with respect to x, treating y as a constant, which gives us 1 times y, or y. We have y equals lambda times the partial of g with respect to x. To find the partial of g with respect to x, we differentiate x plus 5y minus 64 with respect to x, treating y as a constant, which gives us 1 plus 0 minus 0, or just 1. And then for our second equation, we have the partial of f with respect to y equals lambda times the partial of g with respect to y. To find the partial of f with respect to y, we differentiate xy with respect to y, treating x as a constant, which gives us x times 1, or x. We have x equals lambda. To find the partial of g with respect to y, we differentiate x plus 5y minus 64 with respect to y, treating x as a constant, and therefore the derivative with respect to y is 0 plus 5 minus 0, or just 5. And our third equation is the constraint g of x comma y equals 0, which in our case is x plus 5y minus 64 equals 0. Notice here we have y equals lambda, and here we have x equals 5 lambda. The next step is going to be to find the value of lambda and then come back and find the values of x and y. To find the value of lambda, we will substitute 5 lambda for x in the constraint equation and lambda for y again in the constraint equation. So performing those substitutions, again, x is equal to 5 lambda, and we have plus 5 times y, and y is lambda, giving us 5 lambda. Let's go ahead and add 64 to both sides, giving us equals 64. Combining like terms, 10 lambda is equal to 64, dividing both sides by 10. Simplifying, we have lambda is equal to 64 tenths, which simplifies to 32 fifths. Now that we know lambda is equal to 32 fifths, we can determine x and y. Notice y is equal to lambda, and therefore y is equal to 32 fifths. And x is equal to 5 times lambda. X is equal to 5 times 32 fifths. Simplifying before multiplying, 5 divided by 5 simplifies to 1. We have x equals 32. So the point where we find the maximum value in the form of x comma y comma z has an x coordinate of 32, a y coordinate of 32 fifths. To find the z coordinate, we need to evaluate the original function at f of 32 comma 32 fifths. Let's go ahead and do that. Which is just x times y, or 32 times 32 fifths. 32 times 32 is 1024. The z coordinate, or the function value, is 1024 fifths, which is actually the maximum function value under the constraint. So this is the point we are looking for where the location of the maximum is given by the ordered pair x comma y, and the actual maximum function value under the constraint is the z-coordinate or corresponding function value. Now you might be wondering, how do we know this is a maximum function value and not a minimum function value? Well, if we wanted to, we could find the second order partials and then perform the second partials test like we did in the previous section. But sometimes for these problems, it is just assumed that what we find is what we are looking for. But let's go ahead and verify this graphically. So the graph of f of x comma y is the surface, and this black space curve is where the constraint intersects the surface given by f of x comma y. And notice how the point that we found is a high point on the surface under the given constraint, and therefore this point does represent a maximum of the function under the given constraint. Let's summarize our findings and state that the maximum value of f of x comma y is 1024 at the point 32 comma 32 under the constraint g of x comma y equals 0. I hope you found this helpful.